It's estimated that over 1.4 billion vehicles are currently in use around the globe, and each one of these vehicles possess a highly visible yet paradoxically underappreciated technology, the automotive coating. These coatings cover around 3,500 square miles of surface area on all the vehicles on Earth, an area equivalent in size to the landmass of Puerto Rico. While paints in general are primarily used for aesthetic purposes, automotive coatings also serve as a protective layer. Modern automotive paint systems can easily function over a decade under constant exposure to the elements, including degrading radiation from sunlight. They're also highly abrasion and impact resistant. This durability, combined with the efficiency of how they're applied, make these coatings among the most successful developments in automotive technology. At the dawn of the automotive industry, early motor vehicles were painted in a manner similar to both wooden furniture and horse-drawn carriages of the time. A varnish-like product was brushed onto the vehicle's surface and subsequently sanded and smoothed. More varnish was applied and refinished until up to 25 layers of coatings were built up. After multiple layers of varnish were established, the vehicle was then polished to produce a shiny finish. Varnishes are generally composed of a combination of a drying oil, a resin, and a solvent. They harden after application as the solvent evaporates through drying or through a curing process that begins once the solvent has fully evaporated. In cured varnishes, this typically occurs as a chemical reaction between the oils in the varnish and the oxygen from the air. The lengthy brushing and sanding process of applying varnishes was not conducive to mass production, and attempts were made by some manufacturers to reduce the application time through dipping and even pouring. However, the process overall was still very manual and labor-intensive, and it was not uncommon for entire coating processes to take over a month to complete before the vehicle was ready for sale, with black typically being the only color available as it was the fastest drying formulation available. Varnishes also lacked the required durability for automotive use, with coating failures occurring within a year when exposed to the elements. They tended to require regular maintenance. The first true automotive-specific coatings would emerge in the early 1920s as a result of an accidental discovery. Throughout the early 20th century, DuPont had emerged as a major manufacturer of cellulose nitrate movie film. In July of 1921, a worker at one of the film plants had left a drum of cotton fibers treated with a nitrate solution out on a loading dock over a particularly warm weekend. When the drum was opened a few days later, a clear, viscous liquid had developed. This liquid became the basis for nitrocellulose lacquer, a product that would become a popular staple of the automotive finishing industry for decades to come. Nitrocellulose lacquer-based coating systems opened up the door to a large variety of color choices. They were also capable of being applied using the recently developed technique of spraying, in which the product is atomized within a stream of air and deposited on a surface in a controlled manner. This process eliminated the labor of brushing, and the resultant finish produced by spraying permitted the coating to achieve the desired surface properties with as little as 3 to 4 coats with little to no intercoat preparation. Nitrocellulose was the first man-made plastic, and it was created in 1862 by Alexander Parks. Parks had treated cotton fibers, one of the purest form of cellulose, with nitric acid and a solvent, in a process similar to that used to produce dynamite. DuPont chemist Edmund Flaherty would go on to refine the use of nitrocellulose dissolved in a solvent to create a system that used a combination of naphtha, xylene, toluene, acetone, various ketones, and plasticizing materials that enhance durability and flexibility to create a fast-drying liquid that could be sprayed. This extremely volatile solvent mixture would evaporate almost immediately, leaving behind a layer of nitrocellulose solids. When additional coats are applied, the solvent mix melts the surface of the previous coat, allowing the fresh coat to bond with it. Nitrocellulose lacquers has the advantage of being extremely fast-drying, and it produced a tougher, more scratch-resistant finish. It also takes pigments and dyes very well, and it can be sanded and polished to a mirror finish. Offering far more aesthetic options, it quickly replaced the previously fastest drying lacquer option based on asphalt, called Japan Black. While nitrocellulose lacquers would quickly be adopted by the automotive industry, the technology suffered from several key weaknesses. The nature of the coating's composition resulted in relatively poor resistance to chemical solvents, hindering their ability to endure acidic environments. They also tended to yellow and experience pigment fade under exposure to UV light, and without the aid of plasticizing additives, temperature fluctuations would cause cracking and eventual flaking off of the coating. Additionally, the chemicals used in these lacquers were hazardous and highly flammable, making storing them in large quantities a safety concern. By the 1930s, the development of alkyd enamel coatings would offer significant enhancement over the properties of existing lacquers. Alkyd enamel coatings, much like lacquer-based coatings, carry a resin and pigment within a volatile hydrocarbon solvent. This resin, known as alkyd, is a complex oil-modified polyester that, once applied to a surface, undergoes a cross-linking reaction. This reaction occurs between the fatty acids of the oil portion of the resin and oxygen from the surrounding air, creating a durable film as the solvent evaporates. Once cured, this film is also highly resistant to chemicals and solvents. Alkyd enamel coatings, like lacquers, can be applied quickly using spraying, and they were capable of producing an effective coating with as few as 2 to 3 coats of around 50 microns each. Catalysts that induce cross-linking, such as cobalt salts, can also be added in order to reduce the time between coats and the overall curing time. Furthermore, alkyd enamels were compatible with organic pigments, opening up an even larger selection of colors over previous coatings. However, the durable glossy finishes produced by alkyd enamels, much like lacquers, were easily degraded by oxidation when exposed to sunlight. This UV exposure would slowly cause colors to fade and the finish to dull. Alkyd enamels, like lacquers, also relied on strong chemical solvents and were equally hazardous to store and use. From the 1930s onwards, the industry had the option of lacquers or enamels as top coats in both solid colors and metallics that contained a metallic reflective flake within them. The development of these synthetic systems had transformed the finishing process of the automobile, from a handcrafted operation requiring many weeks to a production line operation consuming less than 4 hours of manufacturing time. Much like how a car's paint isn't just one simple layer but a complex, multifunctional system, the news we consume is often the same. In today's information landscape, it can feel like we're only seeing the colorful headline designed to get our attention, while missing the true foundation of a story that lies underneath. Reconciling these different layers to see the bigger, more complete picture is the exact reason I use Ground News. They're a website and app on a mission to give readers an easy, data-driven, objective way to read the news. Every day, they pull thousands of articles from around the world and organize them by story. They also show you the political bias of a source, and with their Vantage plan, you can also see the factuality rating and even the ownership of each news outlet, giving you crucial context about the information you're consuming. It doesn't try to give you an unbiased source. Instead, it gives you the tools to see and understand the existing biases so that you can form a more balanced and independent perspective. In an era of algorithmic echo chambers, this puts the control back in our hands, ensuring that your conclusions are actually your own. Let me show you how it works with a real-world example. Take this recent story about China's push to attract global tech talent. The first thing I see is the coverage detail, how many sources from across the political spectrum are actually reporting on this and who owns those sources. But here's where it gets powerful. When you compare the headlines, you see how differently the story is framed. Notice the difference in language? Now, this source on the right describes this as challenging to the US, linking it to tightening immigration policies while emphasizing it as a direct threat to American dominance, while sources on the left frame this as China gaining a job-creating edge on the global stage, implying a need for US adaptation. Seeing the divergence instantly neutralizes the emotional spin, allowing you to filter out the persuasive language and focus on the raw facts of the event. This is why I rely on Ground News. Accurate research is everything, and this platform is the most efficient tool I've found to cut through the noise. To subscribe, go to my link, groundnews.com/newmind, or scan the QR code right here on the screen. You'll get 40% off the unlimited access Vantage plan, the same one that I use. That link is also in my description and pinned comment below. Supporting Ground News supports independent journalism and my work too. In the 1950s, a new acrylic binder technology would be introduced that would transform the automotive coatings industry. Acrylic paints are based on polyacrylate resins. These synthetic resins are produced by the polymerization of acrylic esters or acrylates, forming a durable plastic film. Like previous systems, the acrylates are dissolved within a hydrocarbon solvent and applied using spraying. However, unlike alkyds, acrylate polymerization occurs without surrounding oxygen, and in most production acrylic systems, is initiated with a catalyst based on isocyanates or melamines. The curing process can also be accelerated by baking the freshly applied coating. Polyacrylate resins do not easily absorb radiation in the solar spectrum when compared to previous resins. They also possess excellent resistance to corrosion, being mostly unaffected by the acids, alkalis, and salts of typical outdoor exposure. Additionally, they're able to tolerate high temperatures, remaining stable well above 150 degrees Celsius or 300 degrees Fahrenheit. These resins also have high transparency, permitting an even broader color range through the additional use of pearlescent pigments, aluminum flakes, and even translucent colored pigments. While most of the automotive coating advances were directed towards the outer layers known as the top coat, the coatings that were used to interface the base metal to the visible layers, known as undercoats, remained relatively stagnant. Since the inception of its use, most of the undercoats or primers were composed of a combination of alkalids and oleaginous resins to produce an interfaced coating. Initially, these coatings were applied to individual panels through dip coating, though this would eventually evolve to a combination of dipping and spraying entire body assemblies. The body would then be baked to accelerate the curing process, and a subsequent intermediate coating known as a surfacer would be applied. This coating contained a neutral colored pigment in high concentrations that could be sanded if needed, providing an ideal, consistent surface for the top coat to adhere to. Because undercoats directly interface to the vehicle's base metal, they serve as the primary form of corrosion protection. However, the process by which they were applied resulted in inconsistent coverage throughout the vehicle. This was due to recesses and enclosed areas on the vehicle's body. In the 1960s, Ford Motor Company would pioneer a dramatically different approach to vehicle priming through electrodeposition. This groundbreaking technique, known as the electrocoating process, involves an aqueous dispersion of a coating carrying either positive or negative ionic groups. The car body is coated on the production line by immersing the body in a tank containing an aqueous primer dispersion and subjecting it to a direct current charge. This causes the dispersed particles to migrate to the vehicle body, with the transfer of electrons creating an electrically neutral film deposition on the vehicle's surface. As the coating builds, a process called electroendomosmosis occurs, where water is displaced out of the deposited coating, leaving a firm surface. The body is then baked to coalesce and cure the primer film. The electrocoating process was not only fast and fully automated, but it also dramatically improved primer film coverage, especially in difficult regions such as recessed areas and sharp edges. It offered far more corrosion protection than previous techniques, and by the mid-1970s, it became the standard of the automotive industry worldwide, and it would ultimately lead to car manufacturers offering far longer warranties against corrosion than previous decades. In the 1960s, the US, starting with California, began to consider the effects of air pollution and centered its concerns on the automobile industry. While the initial regulations focused on automotive emissions, attention soon shifted to automotive assembly plants and the solvent emissions produced from the painting process. By the end of the 1970s, the EPA had sought to reduce photochemically reactive hydrocarbon solvent discharges from industrial finish operations by introducing emission requirements that restricted finishes to be sprayed at a minimum volume solid content of 60%. These requirements led to the gradual elimination of low solids, solvent-borne lacquers and enamels, and looked towards new technologies based on high solids coatings. This initiative led to a new approach to how automotive finishes were utilized, with specific functions of an automotive coating now being directly engineered into each layer. In the late 1970s, the first wet-on-wet systems were developed that consisted of a thin base coat and a thicker clear coat. In this system, a thin pigmented enamel base coat was first applied to establish color, followed by a clear enamel coat. Known as base coat clear coat, the system allowed durability and weathering resistance to be primarily engineered into the clear coat, while the base coat only served as a pigment layer with no inherent protection. The clear coat would be applied directly above the base coat before curing, bonding to it, and forming a single coating. This separation of coating functions now allowed for completely different chemistries to be employed between layers. In the early 1970s, General Motors had introduced the use of the first water-borne enamels. Based on solvents composed of glycol ethers and water, these systems dramatically reduced hydrocarbon emissions and were generally high solid in nature, easily meeting EPA requirements. However, these systems had sensitive application characteristics, requiring air conditioning of the spray booths, and initially they produced a low-quality finish and were generally more expensive to apply. As waterborne technology evolved, it would find its ideal application as the base coat layer for production base coat clear coat systems. These low-solid, waterborne base coats were heavily pigmented and could be applied in films as thin as 15 microns, while still having an excellent appearance with low emissions. These more advanced waterborne coatings developed as a result of the introduction of new coating chemistries based on polyurethanes in the 1980s. Polyurethanes are a class of polymers composed of organic units joined by carbamate links. Polyurethanes are formed from a reaction between isocyanate and organic compounds called polyols, and while they can produce extremely hard and durable films as a coating, they lack some key properties needed for automotive use. Modern automotive coatings overcome these limitations by using a hybrid dispersion of acrylics, polyurethanes, and polyesters. These systems, known as acrylic polyurethane enamels, incorporate the monomers of each resin in a proprietary combination that, once initiated by a catalyst, undergo polymerization. Because each resin's polymerization reaction is incompatible with the other, an interwoven, mechanically interlocked polymer network is formed. By adjusting the constituent resins and their quantities, as well as the catalyst formulation, the sequence and rate of how this polymer network is formed can be modified, and the properties of the composite film adjusted to suit the needs of the product. Primers, for example, are formulated to produce a larger proportion of polyester resin in order to create a higher building film, while base coats are designed to form a high pigment retention film. Clear coats, on the other hand, are engineered to be tough and chemically resistant while providing UV resistance through the inclusion of ultraviolet light absorbing additives and chemicals known as hindered amine light stabilizers, or HALs. By the turn of the century, modern automotive coating methods have brought complete finish application time down to as little as 12 hours on high-volume assembly lines. In general, this highly automated process occurs in 5 steps. In the first step, called pre-treatment, the freshly welded vehicle body goes through 3 primary liquid dip processes of degreasing, conditioning, and phosphating. These cleaning baths remove contaminants from the welding process, as well as help the primer to bond onto the metal. In the phosphate treatment, a thin, dense, and uniform phosphate conversion layer is deposited to provide protection against corrosion. In the next step, the automobile body is lowered into an electrodeposition tank containing around 80 to 90% ionized water and a mixture of resin, binder, and a paste consisting of pigments. An electric current is applied to the vehicle body, and the deionized water acts as a carrier for the paint solids, depositing it on the vehicle's surfaces. As the coating grows in thickness, it becomes more and more insulating, slowing down the process. After coating, the vehicle body is then baked at 160 degrees Celsius or 320 degrees Fahrenheit for around 10 minutes, leaving a 15 to 25 micron film that serves as the vehicle's primary defense against corrosion. At the next step, urethane or PVC-based sealers are applied throughout the body in highly specific locations for the purposes of anti-corrosion, the elimination of water leaks, and to reduce vibration and noise. This step may also include underbody coatings and is typically automated by the use of robots. The fourth coating step is the application of a primer surfacer, or simply primer. The system used in this step can vary from water-borne to solvent-borne, or even a dry powder that is baked. This 30 to 40 micron thick film functions as a leveler that produces a smoother finished surface, while also providing additional protection against corrosion and creating an ideal adhesion interface layer between the electrodeposition coat and base coat, increasing the top coat's durability. In the final 2 steps of the body coating process, the top coat is applied. The base coat containing the pigment is first applied in a thin film of just 15 microns, followed by a 30 to 40 micron thick clear coat. The clear coat is applied after a brief flash-off period after the base coat, and once application is complete, the entire vehicle is baked at 125 degrees Celsius or 257 degrees Fahrenheit for 30 to 40 minutes to accelerate curing. The application of these top coats occur within spray booths that include air handling systems for temperature, humidity, and cleanliness control, as well as paint and emission capturing equipment. Control of the application environment is especially critical for the base coat layer, as most manufacturers now employ highly sensitive water-borne base coats. The top coat spraying process of modern assembly lines is also heavily, if not fully automated, by robots. The automotive industry has brought coating technology to a level of efficiency and effectiveness that would have been inconceivable at the dawn of automotive mass manufacturing. With over 40,000 manufacturer color and texture variations in use today, modern coating systems bring an unprecedented level of quality and durability while being both cost and time efficient and meeting rigorous environmental regulations.